Hello everyone, welcome to GATE Pass. So I'm going to solve in this video remaining problems of year 2017 that were related to thermodynamics. So the first problem which I have selected is question number 48. It is based on chemical reaction equilibrium. We have already seen twice the problems of chemical reaction equilibrium, but that involved gas phase. So this question, it is the reaction which is taking place in a liquid phase. So what you have is, this is tertiary butyl alcohol, tert-butyl alcohol. It is reacting with ethanol to give you ethyl tert-butyl ether plus water. Okay. Further information what they have given is that the molecular weights of these compounds have been given. Okay, to start with, they say that you have tert-butyl alcohol. How much you are using? 74 grams. Okay, I should write properly. So it is 74 grams. Since molecular weight is 74 gram per mole, so I have converted that initial number of moles is 1 mole. Then they said that you are using a aqueous solution of ethanol, in which ethanol is 46 weight percent, and how much you are using? 100 grams. Okay, so 100 grams of aqueous ethanol is used, which has 46 weight percent. So to start with, you have 46 grams of ethanol. Okay, and the remaining is water. So how much is water? To start with, you have 100 minus 46, that is 54 gram of water, and there is no product being formed initially, so you have initially 0 grams of your product ETBE. Okay, so now 46 grams, its molecular weight is 46 grams per mole, so initial number of moles is 1. Initial number of moles for this is 0. For water, you have to start with 54 grams. Now you know that your molecular weight of water is 18, so 54 divided by 18. To start with, you have initial number of moles for water as 3 moles. Okay, so this calculation I have done very quickly. Now the equations which we are going to use, I have listed them over here. So this is product over all I, xi raised to nu I, that is equal to k. K is the equilibrium constant, which they have given the value as 1. Okay. Now, what is nu I? Nu i's are nothing but the stoichiometric coefficients which appear in this reaction, and summation of nu I, that is what we are calling as nu. So, summation nu I, let's find minus 1 plus 1 plus 1. So, basically your summation nu I, which we denote as nu, that is equal to 0. This equation you have already seen in last videos, couple of videos. So there we had written the mole fraction in the vapor phase. Here again we can write my mole fraction in the liquid phase as in terms of your extent of reaction, or the reaction coordinate epsilon. Okay, so epsilon is nothing but the extent of reaction. Now let's quickly see how do I get this equation. Okay, so we had seen previously also that when you apply your criteria of chemical reaction equilibrium, then after solving it, what you get is this equation. Okay, let's go through what are the different terms in this equation. So your Fi cap is your fugacity of species I in solution. Okay, what is Fi naught? That is the fugacity of pure liquid I at system temperature and pressure equal to 1 bar. So we are defining our standard state as the state of the pure species at system temperature and the pressure of 1 bar. So that is your fugacity in the standard state. Now we can write the fugacity of species I in solution as gamma I xi Fi, where Fi is nothing but the fugacity of pure species I at the system temperature and pressure. Okay, so I am going to put the values of this Fi cap, I am going to put in this equation, and then I write gamma I xi Fi upon Fi naught. Okay, now this fugacity is for pure species at system temperature and pressure, and this fugacity is for pure species at system temperature and standard pressure of 1 bar. For liquids, keep in mind that the fugacities, they are weak functions of pressure. Okay, so you can take the ratio of Fi upon Fi naught as 1. Okay, so then this thing you can cancel. So what you are left with is gamma I xi raised to nu I. Again, if we assume that this reaction mixture, it behaves like an ideal solution, then my gamma I also I can assume 1. So I am left with now this equation. Okay, rest of the problem is very simple. Quickly you can find out what are your xi's, then put it in this equation and solve for extent of reaction. That will give you how much reaction has taken place. Then the question has asked you how much of this compound is formed at equilibrium. So let's do it. I will erase all this background over here and I will solve over here. Okay, so let's first write down what are the mole fractions of different components. For simplicity, I will say that this is component A, this is component B, this is C and this is D. Okay, this is the terminology I am going to use. Then I can write mole fraction of XA, that is equal to initial number of moles 1 minus, because nu is minus 1 over here, epsilon upon, okay, this term goes to 0 because your nu is 0, so divided by total number of moles initially which are present, so 1, 1, 2 plus 3, 5, so it is divided by 5. Similarly, your xb will be equal to your 1 minus epsilon divided by 5. xc is equal to, initially you do not have any this thing, so 0 plus epsilon divided by 5. Your xd, that is equal to, initially you have 3, so 3 plus epsilon divided by 5. Okay, so you can quickly write down your mole fractions in terms of your extent of reaction. Now put this in equation. So your K, that is equal to, first of all, because products will be raised to plus 1, so I am going to write epsilon by 5, 3 plus epsilon by 5. Now reactants, they will have a they will be raised to power minus 1, so I am taking it in denominator and I will have 1 minus epsilon by 5 into 1 minus epsilon by 5. Now 5 throughout will cancel, this value is equal to 1, so I have epsilon into 3 plus epsilon, that is equal to 1 minus epsilon whole square. Okay, so up till this point everything is fine. Now let's go over here, solve this equation. 1 minus epsilon whole square, I will open this bracket, so it's epsilon square minus 2 epsilon plus 1, that is equal to 3 epsilon plus epsilon square. Now epsilon square will cancel from both sides, LHS and RHS, and if I take it over here, so it will be 5 epsilon is equal to 1, or epsilon is equal to 1 by 5, that is equal to 0.2 moles. Okay, so it was very simple. You got your extent of reaction. Now you have to find out how many moles have been formed. So for ETBE, so that will be equal to number of moles formed will be equal to, I am going to directly write initial number of moles is 0 plus nu I, that is 1 multiplied with 0.2, that is equal to 0.2 moles are formed. So this is the number of moles of ETBE, so I will just write NC. Okay, so the number of moles of ETBE which are formed at equilibrium is 0.2 moles. Converted into mass, because they have asked the answer in terms of mass, so here mass of ETBE, that will be equal to 102 into 0.2, and that will be equal to, calculated, so that is equal to 20.4 grams. Okay, and this is your final answer. Okay, so the next question which we are going to take is question number 34. It again appeared for 2 marks. They have given that the vapor pressure of pure substance at some temperature T is 30 bars. The actual and ideal gas values of G by RT for saturated vapor are given as 7.0 and 7.7 respectively. Okay, now they have asked you to calculate what is the fugacity of saturated liquid at these conditions. So in this problem they have asked you to calculate the fugacity of saturated liquid, but all the data which is given, you can calculate the fugacity of saturated vapor. So what we are going to assume is that the saturated vapor and saturated liquid, they are in equilibrium at the temperature which is given and the pressure 30 bar, and we will calculate the fugacity of saturated vapor and then assume it to be equal to the fugacity of saturated liquid. Now the fugacity of saturated vapor can be calculated by making use of the residual property, which is nothing but the actual minus the ideal. So actual G by RT minus G by RT of ideal, that is given as GR by RT. You have this equation GR by RT, that is equal to ln of phi, where phi is your fugacity coefficient. But this is a simple equation to remember. Now you have your GR by RT, that is equal to ln of Fi by T. You have to find Fi, everything else you know. So what is GR? That is equal to G actual upon RT minus G ideal upon RT, that is equal to ln Fi by P. Put the values, 7 minus 7.7, that is equal to ln Fi by 30. Okay, minus 0.7. If I take ln on this side, then it will become exponent raised to minus 0.7, that is equal to Fi by 30, or your Fi will be equal to 30 times exponent minus 0.7. Okay, do this calculation and you will get the value which is 14.89 bar. They have asked you to report it to first decimal place, so round it off, it is 14.9 bar. So this is your answer. Okay, so the third problem which I am going to take is question number 32. It appeared for 2 marks. So the problem statement, it goes like this, that the pressure of a liquid is increased isothermally. Okay, so it's a constant temperature process during which the molar volume of the liquid decreases from V1 to V2. The numerical values are given. The isothermal compressibility kappa is given as 10 raised to minus 9 per Pascal. Okay, and it has been assumed to be independent of pressure. Change in the molar Gibbs free energy of the liquid is what you have to calculate, and you have to give the answer in joules per mole. Okay, you have to calculate your change in molar Gibbs free energy, which is dG, where G I am now referring to as my molar Gibbs free energy, that is equal to minus SdT plus VdP. Okay, since this process is taking place at constant temperature, then my minus SdT term, it goes to 0. What I am left with is dG is equal to VdP. Okay, now in order to find the change in the molar Gibbs free energy, I have to integrate this equation, but I don't know, like there is no information which is given about P. Okay, the only information which is given is about V. So I will change the variable with respect to which I am integrating from P to V, and for that I will use this equation. Okay, since this is taking place at constant temperature, so I can equally will write it that kappa is equal to 1 upon V dV upon dP. Okay, this is small v. Now let's find out dP in terms of dV. So I write dP, that is equal to minus dV upon kappa into V. Okay, now change the variable with respect to which you are integrating. So I will put in terms of V. So I get integral V dV upon kappa into V. Of course there is a minus sign. V gets cancelled. So I have to integrate from V1 to V2 dV upon kappa. So what I get is minus V1 minus V2 upon kappa, and that will give you your change in Gibbs free energy. Do this calculation, very simple. Okay, so V1 minus V2, I have absorbed the negative sign in it. Okay, so V1 minus V2, 50.45 minus 48, that is 2.45. So 2.45 into 10 raised to minus 6 divided by 10 raised to minus 9. So that is equal to 2450 joules per mole. Okay, so this is your answer. So it was a very simple problem. Okay, just you have to remember that you have to find your change in molar Gibbs free energy. Write down the equation, simplify it for the given conditions, and then VdP, because this value is given, so I am changing my the variable with respect to which I am integrating. So from dP to dV using this equation, putting it over here, integrating it, and numerically it's a very small problem. Okay, so I hope you understood, and if you like my video, please don't forget to subscribe to my channel and like this video. Thanks for watching.